Morning, everyone. Morning, Papil. Morning, Mas Hendra. Good morning, Pak Zul.
Morning.
Good morning, Pak Andri. Good morning, Pak Phil. Good morning, Pak Hendra.
Nice to meet you again.
Nice to see you.
Hey, Pak Phil,
Long
how are you?
time. I'm good. How are you?
I'm fine, and you?
Yeah, long time no see. I'm good.
Yeah. Good.
So you can hear me okay?
Okay.
Yeah,
Very
clear.
good.
Excellent.
Very good.
Excellent. Good.
Did you hear me okay?
Yep.
Very good, Pandri.
Okay, thank you. Actually, I'm from office.
Wow.
All right. I'm from home, as you see.
Okay. Yeah. Okay. Papil, sorry about the paper of the Lombok earthquake. Actually, already published. I will send you the paper.
Okay. Yes, please. I'd like to see it.
Okay. Thank you. Pak Zul is very busy recently as committee, as the chairman.
Yeah.
Good luck. Thank you, Pak Zul.
Yeah, you're welcome, Pak Andri.
Thank you.
Thank you, Pak Phil, for accept our invitation to give a talk today.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. I welcome you all to our third Southeast Asia Conference on Geophysics 2020. I hope you all have a good day, healthy, and maintain your high spirit, and always stay safe in this pandemic condition, in this condition that we have never experienced before. Probably in ITB, we already stay at home for more than 6 months already. Instead, we have to keep cheerful always. So for this morning, please allow me, I'm Endra Gunawan, to be the moderator of this panel discussion 2. The topic for this panel discussion 2 is future perspective on seismology and geohazard mitigation. The presenter for this morning session will be, the first is Professor Dr. Phil Cummings. He is from Australian National University. And then the second presenter will be Professor Dr. Andri Dianugraha from Institut Teknologi Bandung. And finally, the third speaker will be Professor Sri Widiantoro, PhD, also from Institut Teknologi Bandung. Each presenter should present their material for 20 minutes, and then we will continue our discussion for the last 30 minutes. We hope that we have a fruitful discussion in this seminar. The first speaker, Professor Phil Cummings, is from Research School of Earth Science of Australian National University. He's been working in many fields, such as tsunami, seismic hazard, seismology. A lot of research has been done also in Indonesia. If we move backward, probably the last couple years, he also involved in the national seismic hazard map. He helped us toward achieving those maps for national purposes. And without further ado, I welcome Professor Phil Cummings to give your presentation for the next 20 minutes. Please, time is yours, Pak Phil.
Thank you very much, Pakendra. I'm trying to share my screen, but it says host disabled attendee screen sharing. Is there something that can be fixed there? I can't share my screen.
Please, the host, can you help Papil to share the screen?
Okay, it's loud now.
Okay, I'll try now. Okay, looks good. Thank you very much.
Okay, thank you. Please, Papil, time is yours.
Okay, all right. So you can see that screen? Okay.
Yes, very
great.
good.
So I'm going to talk about earthquakes and tsunamis caused by low-angle normal faulting in the Banda Sea in Indonesia. And I've listed these co-authors. This work appeared in a recent article in Nature Geoscience with these co-authors. You can see that myself, Riam Pranancha was my PhD student from ANU, but he was originally from ITB. And then also, I'm sorry, Irwa Milano. Oh, I missed him. Yeah, he's from ITB. And he was also a co-author on this work. He should also appear there, Dr. Irwa Milano. My apologies if he's in the audience. He should also appear on that author list. Okay, let me move on. Yeah, okay. So we all know that submarine trenches are associated with subduction zones. And if you look at a global map of bathymetry and you look at these dark areas, which are areas with ocean depth of 7,000 meters or more, they illustrate the marine trenches. And you can see them all here. These are all where the subduction zones are, where one tectonic plate is slipping beneath another, and the dynamics of that results in this pronounced deep trench along the subduction zone. So I think we're all very familiar with that, and I don't need to explain it. There's only one place in the world, I believe, where the ocean depth is greater than, well, roughly 7 kilometers deep, but it's not actually associated with the subduction trench. And if you look carefully at the really dark areas of this bathymetry, you can see where that is. It's in the Banda Sea, and it's known as the Weber Deep. So I'll explain now that that is not actually associated with the marine trench, with the kind of subduction zone that we normally associate marine trenches with. This is a more sort of detailed map of the Banda Sea, and you can see the Banda Arc wrapping around here. Let me see if I can get my pointer, laser pointer. Yeah. You can see the outer arc of the Banda Sea around here, which is often written as a subduction zone, but you can see that that's not where the deep marine trench is. The really deep ocean trench is actually inboard of that. It's called the Weber Deep, and it's actually between what's called the inner Banda Arc and the outer Banda Arc. But it's not where we normally draw the subduction zone. In a normal subduction zone, the marine trench would be here along the Banda Outer Arc. And this is quite different, and it should be telling us that there's something unique and very unusual, very unusual that is happening here in the Banda Sea. Now, this has been interpreted in the past. This remarkable arc, this outer arc of the Banda Sea, has been interpreted in the past in various ways. One is that you have basically two slabs subducting, one from the north subducting southward along the Saram Trough here, and one from the south subducting, the Australian plate subducting from the south northward along the Timor Trough here. And so you can see this is a paper by Cardwell and Isaacs, an old paper, 1978, and you can see these sections of seismicity going from, let's see, this is Saram in the north to Timor in the south, so this is N7 over here, and basically moving eastwards towards the end of the Banda Arc here. So you can see these, what are thought to be two slabs subducting from the south and from the north here and here and here. And so that's been, some people still regard that as the explanation for this pronounced wrapping around of the arc, but there are some problems of this. Before I get to those problems, I want to point out that there are very few shallow earthquakes in the Banda Sea itself, in the middle of the Banda Sea here. All of the earthquakes generally are fairly deep because they're thought to be intraslab earthquakes. All of the recorded catalog earthquakes are generally pretty deep. Very few shallow earthquakes until you get to the very eastern end of the arc over here. However, in the historical experience of earthquakes, there have been devastating earthquakes in the Banda Islands themselves, in the middle of the Banda Sea. And these were devastating. I mean, they really, the comments are here, 1683, most houses became rubble heaps. 1710, most houses were damaged irreparably. 1763, 3/4 of all houses transformed to rubble. So there was clearly very strong shaking in the Banda Islands that resulted in widespread destruction in those islands. So none of those are typical of intraslab earthquakes. And in fact, I'll get to that. I'll get to that later. But none of this is really, these were felt strongly and were accompanied by ground shaking, fissuring, and tsunamis, and prolonged aftershocks that were felt in the Banda Islands themselves, which are not typical of intraslab earthquakes. So in any case, these historical events, because they appear to be very large and had lots of ground shaking and strong tsunamis, were interpreted as having been associated with massive megathrust earthquakes along the Banda Outer Arc. And you can see this was a paper by Lewin Harris and Harrison Fisher for the 1629 earthquake and the 1852 earthquake. And you can see these are massive earthquakes. These are the seafloor deformation calculated from massive megathrust events along the Banda Outer Arc to the north along the Saram Trough and the south sort of along the Timor Trough. I won't bother showing the animations of those tsunamis, but they generated large tsunamis. And also, it's thought that they generated this very large ground shaking. This is in particular for the 1852 earthquake. There's a really wide area where this earthquake was felt. So you can see that the strong shaking was felt at Banda Nera, but it was felt all the way into East Java and all the way up to Ternate. And in addition, there was this small islands that appeared in the year, that were noticed in the year after the earthquake and are thought to have appeared at the time of the earthquake. So this would seem to indicate that it was a uplift associated with the megathrust rupture. So that seems to indicate where the rupture area was. And then you had this huge felt area all throughout eastern Indonesia. So yeah, clearly, a very large earthquake if it was a megathrust earthquake. Now, so they did modeling of these tsunamis, and they were able to come reasonably close to explaining the tsunami height observations around Ambon and Haruku, as well as in Banda Neira itself. They didn't really get quite that big as the ones that were observed in Banda Neira. This was an 8-meter tsunami observed in the channel, but there were several meters. There were very large tsunami observed throughout the Banda Sea. But there are some problems with this, and that is associated, that you can see from here. Here's an animation of what happens in a subduction zone earthquake. And if this is the Banda outer arc, this would be the Banda Sea here. And what you see is that when the earthquake happens, the earthquake is such as to give a trough first and crest first motion. And so you can see that, in fact, the megathrust tsunamis that were calculated here have this trough first motion. But that's not what was observed. Anywhere in the Banda Sea, you'll see this just by virtue of the geometry, that the Banda Sea would be over here. That will result in the tsunami being an initial drawdown. And that's not what was observed historically. In 1852, the accounts clearly indicate a positive going first wave. So it was a positive motion of the sea level, not a drawdown. So that is the first indication that there is some problem with this megathrust earthquake hypothesis. In addition, there were problems with some of the observations. First of all, this island that appeared is almost certainly associated with a mud volcano. The Kekachil Islands are known for having mud volcanoes. They can appear spontaneously, or they could be triggered by an earthquake at considerable distance. So this does not require, the appearance of this mud volcano does not require that the earthquake rupture area is right in that area. The earthquake could have been some distance from that mud volcano. We saw this happen. At least there were credible arguments for the Lucy mud volcano being triggered by the Jogjakarta earthquake quite some distance away. There's also instances in the Makran subduction zone in the Arabian Sea where mud volcanoes at hundreds of kilometers from earthquakes have been triggered. So this does not require that the rupture area be in the Tanimbar Trough. And also the observations in East Java have recently been associated, rather than with this 1852 earthquake in the Banda Sea, with a smaller earthquake on the Pasuruan Fault in East Java. And this was in a paper by Marliani et al. In 2019. So that really changes our view of this 1852 earthquake. The other thing, though, which I think is in some ways the strongest argument, is that there's 250 kilometers between this supposed megathrust rupture area and Banda Neira. And if you look at what the ground motion would look like for even a large megathrust earthquake at 250 kilometers distance, that's going to result in only light shaking. You're not going to get strong, severe shaking that would result in this widespread damage. I just don't think, given those accounts, which very clearly indicate that there's widespread destruction in the Banda Islands, I don't see that you could get that from a megathrust earthquake at 250 kilometers distance. So that's another problem with this megathrust earthquake hypothesis. Now, but a more sort of fundamental argument is based more on the tectonics. And this, as I mentioned, that this Banda outer arc has been thought to have been due to two slabs subducting, one from the north and one from the south. But there are real problems with that hypothesis. One is that there's no evidence for consumption of oceanic lithosphere along the Saram part of the arc. If there had been a lot of subduction happening there, we should get indications that a lot of oceanic lithosphere had been consumed, and we should see remnants of that in Saram, and it's not there. And then the other, of course, is the suture between the two plates, the southward and northward subduction. There just isn't clear geologic evidence for that either. So around 2010, Robert Hall and Wim Spakman came up with an alternative hypothesis for this, and that is that subduction, the Australian plate was subduction northward. So here we're looking from the north to the south, across from Ceram towards Timor, and you can see the subduction of the Australian plate is occurring here. And as that proceeded, what you got was the slab rolling back into what's called the Banda embayment. There's this embayment in the Australian plate, which is oceanic lithosphere, and the slab at this point just starts to roll back, and it just starts to fall back into this embayment. So there's no longer pushing of the Australian plate at these subduction zones. The slab is simply rolling back into this embayment until we get the present configuration here. And that's how we got this strong curvature. It was due to a pre-existing structure associated with this Banda embayment. It wasn't due to two slabs converging or even to one slab being wrapped around. It was simply due to the slab just rolling back, just falling back through its own weight into this pre-existing embayment that you can see right here. And that really changes our picture of what the nature of that plate boundary is. Because as a typical subduction zone megathrust, you have a plate, an oceanic plate that's been subducting for tens or over 100 million years. So you can get hundreds of kilometers of displacement accumulated along this major plate boundary. It's got very shallow dip with a particular structure, both compositional and thermal structure, that will result in strike-slip friction active over a very wide downslip range. And that's why you get these massive earthquakes on a subduction zone megathrust. What we have with this rollback hypothesis is completely different. What you have instead is extruded in the Weber Deep here. You have material that's been extruded from the lower crust and even uppermost mantle to actually form the Weber Deep. And that's getting pushed out towards the Banda arc, where you get this much more smaller sort of fold and thrust belt. So this Weber Deep's about 180 kilometers. It is 180 kilometers wide. It's formed over the past 2 million years. So that means you get about 6 centimeters per year of displacement along this what is a normal fault on the inner arc, along the inner arc. So all of this displacement that you got to form the Weber Deep is due to its displacement here, not here. So all of the recent long-term fault displacement is actually happening in a normal sense along the western side of the Weber Deep, not over here along the Banda outer arc. And we can see this a little more clearly here in this sort of cartoon that's mainly done by my co-author, Jonathan Pownell, and his colleague, Robert Hall. So you can see the Banda slab sort of falling back into this embayment. And so you're getting all this material that's been extruded to form the Weber Deep and is sort of pushing up. You do get thrust faulting here, but it's much less extensive. It's not like a big megathrust. It's just a fold and thrust belt. And all of this fault displacement to form the Weber Deep is happening here at this, what's now called the Banda detachment, which is thought to be a huge normal fault right underneath the Banda Islands. And you can see spectacular examples of some of this normal faulting. What this is saying is that the active tectonics in this area are more extensional than they are compressive. And you can see spectacular examples of these normal faults. These are actually along some islands along the eastern side here, where you see these normal fault scarps, beautiful, fresh, normal fault scarps formed here. You can see the footwall here is a peridotite and gneiss, so that's lower crust or even possibly uppermost mantle material here, and that's what's formed the footwall of this normal scarp, normal fault scarp. That makes a lot of sense now if we now associate earthquakes with this normal faulting in the inner Banda arc. That actually makes a lot more sense in terms of the ground motion, because it would mean that we could have an earthquake that's much closer to the Banda Islands, and that's how you could get this very strong ground motion that would cause widespread destruction in the Banda Islands. And if you take a look now the earthquake has a much less extensive felt area, which very high intensities in the Banda Islands, which fall off very rapidly. And these brown, this is rupture distance here versus observed intensity, and these orange dots are what we interpret now based on a magnitude 7.5 earthquake on or near the Banda detachment, right near the Banda Islands. And you can see that this is a ground motion model here, and these dots are the observed intensities. And you can see that fits the data a lot better than you can fit it using a megathrust model, which is this blue here, where this is the same data. These blue dots are the same data, but they're plotted at different distances because the earthquake's in a different location. So you can see that these blue dots do not fit the ground motion very well, the blue ground motion very well at all, whereas the orange dots do fit the orange ground motion model much better. So this really makes a lot more sense to have that kind of widespread destruction in the Banda Islands. You need an earthquake really close to the Banda Islands. And if you do that, the earthquake is likely to be much smaller. Now, what about the tsunami? The odd thing about the tsunami is that it arrived 15 minutes after 5 minutes of strong shaking. So it arrived about 20 minutes after the initiation of the earthquake. So if we draw what are called the tsunami inverse travel times curves from Banda Neira, that will tell us where this tsunami would have initiated given a 20-minute travel time. And here's the 20-minute contour here. So you can see it crosses this Banda detachment. This is the Banda detachment, crosses it here. And it also crosses the toe of this huge submarine landslide on the eastern side of the Weber Deep. So these are our two possibilities, is to have a very large earthquake down here along the Weber Deep, along the Banda detachment on the western side of the Weber Deep, or the earthquake could have triggered a landslide. And to make a long story short, this really doesn't fit very well. We did a lot of modeling, trying to model an earthquake here, but it really has to be very, very shallowly dipping. It has to be a very large earthquake on a very shallow dipping fault, and it just doesn't make sense. You still can't fit the data. We'll see, but I'll show that in a minute, but it really doesn't fit the tsunami data well at all. So we think what's happening is the earthquake here, very close to the Banda Islands, triggered this massive, or at least part of this submarine landslide over here. And so if we look at that, here's our tsunami modeling, and you can see that these are the tsunami this modeled tsunamis of Banda Neira at Ambon and Saparua. You can see these are the sources for what's a Banda detachment to the south of Banda Neira. This is the huge Tanimbar Trough source over here, and that's in the red here. This one is the green here, I believe. Isn't that right? Let me see. Yeah, no, I'm sorry, I got it wrong. Green is the Tanimbar Trough earthquake, this source here. The red is the Banda detachment, so it's this source here. And the blue is the submarine landslide. So you can see that it's really the blue one that produces this huge tsunami in Banda Neira, consistent with the observations. It's got both this and the Banda detachment produce positive going waves everywhere, unlike the Tanimbar Trough earthquake, which always produces a trough and is much smaller. So bottom line is that it's really the landslide that explains the tsunami data. It was the landslide source explains both the polarity of the tsunami data as well as its amplitude. It explains it much better than any of the other sources. So how likely, we might ask, was this to have been triggered by an earthquake? 250 kilometers distance from a 7.5 earthquake. There are a few systematic studies of submarine landslide triggering, but there was one done for the east coast of the U.S., which we drew on, and it did find that a magnitude 7.5 earthquake could trigger earthquakes in poorly consolidated submarine sediments at 250 kilometers distance. If the dip of the sediments was about 6 degrees, that was the critical dip. And so you can see here, these are cross sections drawn through the Weber Deep, and you can see in many cases the maximum dip is greater than 6 degrees. Here it's 6.6, 9.5, and 9 degrees. So clearly there you do get some very steep dips, and they could have resulted reasonably. It is reasonable to infer that they could have resulted in mass failures with a 7.5 magnitude earthquake at 250 kilometers distance. So it seems reasonable to trigger an earthquake at that distance with an earthquake that big. What about some of the other events? You know, that this was not the only event for which a large earthquake was accompanied by a tsunami, and it's quite mysterious to some extent that some of the other events have tsunamis with different polarity that have an initial drawdown rather than a positive going wave. And so, and in that case, they arrived much more quickly. I think it was within 5 minutes or so. And that is actually explainable with this landslide model, because you do get other landslide scarps on either side of the Weber Deep. You get some smaller landslide scarps, and in this case, there's one on the western side. So this would arrive much earlier at Bandinera, and it would have opposite polarity because the landslide's going in the opposite way. So I think you could explain some of the other events also in Bandinera by similar earthquakes associated with the Weber detachment that trigger landslides along the edges of the Weber Deep. Okay, now if this is happening, if we're getting this rollback and you're getting this this rapid movement, 6 centimeters per year, very fast opening of this Weber Deep, and that's being accommodated on this Weber detachment, you should get all of the Banda plate sort of moving, being sucked eastward by this slab rollback. And we were asked to do this by a reviewer to look at the GPS data, and we developed a tectonic block model, which I'm not going to explain. You can ask about this if you want. It's a fairly complicated explanation. So in the interest of time, I'm just going to move on and say, this is our explanation of the GPS data. So you can see here, these are GPS measurements in the inner arc and the outer arc. And you can see these are the black are the vertical movements. The green and red are the horizontal movements, which were only available in the Banda Islands. And so having a Banda detachment with 6 centimeters per year slip over here actually produces the observations pretty well. So it's consistent with the current observations of crustal movement in the inner arc, whereas the outer arc is consistent with smaller thrust faulting associated with the thrust and fold. Okay, so I'm going to finish up. I think my time is up. So my conclusions are that destructive historical earthquakes in the Banda Sea were likely caused by earthquakes associated with Banda detachment. It's unlikely that giant megathrust earthquakes occur on the outer arc megathrust because we don't think there is a megathrust on the outer arc. We don't think that is a megathrust. Destructive tsunamis were likely generated by submarine mass failure along the edges of the Weber Deep. And these were triggered by the earthquakes, but you could get them potentially occurring spontaneously. And the Banda plate resists accommodation of the extension associated with slab rollback. Did this result in formation of the Weber Deep? That's a question. I didn't really explain that because I had to go into the tectonic model. You can ask about that if you want, and I can explain that in more detail. So I'm going to now end my talk. I think my time is definitely up, so I'll pass on to some of the other speakers. Thank you very much for listening.
Thank you very much, Pak Pil.
I will stop sharing.
Very interesting result and also informative. Okay, if anyone who want to pose question, please write down in the chat menu. If you want to be anonymous, you can send privately to me, and I will deliver the question later in the final 30 minutes of this session. So I hope you stay in the webinar, Pak Pil.
Okay, I will
for
do.
Another 40 minutes after
Absolutely.
Pak Andri and Pak Ilik. Thank you, Pak Pil. And now we will move on to the next presenter. The second presenter will be Professor Andri Dianugraha. He is considered as from the geophysical engineering, and he received his professorship on 41st years. So, and then he also the former president of Indonesian Association of Geophysics from 2018 to 2020. And without further ado, I welcome Pak Andri to share his research for the next 20 minutes. Please, Pak Andri, time is yours.
Thank you, Pak Endra. May I share my slide? Okay.
Please.
Okay. Can you see my slide, Endra?
Yes, Pak Andri. Very clear.
Okay, thank you. Sorry, Pak Pil, I am not English native, so my English is not so good. But I will try. Okay, good morning, everyone. So I am Andri Dianugraha from Geophysical Engineering, Faculty of Mining and Petroleum Engineering, Institute of Technology, Bandung. Today, I would like to present our results about the local earthquake tomography around the source region of the moment magnitude 6.5 Ambon earthquake Indonesia, 26 September 2019. Actually, this study is collaboration with BNPB, BMKG, BPBD, Universitas Patimura, and also TNI, and also Pemprov Maluku. Yeah, you can see here. This is our teams. Pepen Supendi from BMKG, Abdul Muhari from BNPB, Pak David Sahara from ITB, ini Pak Andi Rusdin from BMKG, and et al. Actually, sorry, many authors involved in this study, including our student also here. Okay, actually, about the Ambon earthquake yesterday, actually, there were some presentation about the Ambon earthquake from researcher from BMKG and so on. So the Ambon Island is located in the north of Banda Aceh, eastern part of Indonesia, that is located in the very active tectonic and complex geological setting, as mentioned by Pak Phil. Yeah. And suddenly in September, actually 26, 2019, yeah, in the morning local time, major shallow earthquake of the 6.5 moment magnitude suddenly shook this region, and which could be felt throughout the island, especially in Ambon Island, Haruku Island, Saparua Island, and Seram Island. And we can see here, this is the location of the epicenter of the main shock, and then causing significant damage and many casualties as reported by authorities. And then we can see here, this is the local mechanism of the event, yeah, from Sofendi et al. Actually, this is from BMKG actually, and this is the BMKG shake map for this event. Yeah, we can see here, strong and significant event. Yeah, and then the objective of our study actually first is to record the aftershock event by using the temporary station and also combined with the permanent station of seismograph from BMKG, and then to determine the aftershock location, moment magnitude, source mechanism, and slip inversion by using this local network. And also in this presentation, I would like to focus to determine the 3D seismic velocity structure, including PP, VS, PP over VS ratio, to infer the fault geometry of the fault. Actually, for the seismicity around Ambon, around Saparua, around Haruku, around Seram, we have tried to search the previous study or geological information about this fault. Actually, not so many. So I would like to try to see the fault geometry by applying the seismic tomography by using the local network combined with the permanent station. And finally, of course, the study attempt to support for the seismic hazard mitigation in Ambon and its surrounding for the current and for the future. Again, we thanks to BNPB for the supporting and BMKG for the for the permanent station and collaboration in the field, for the Indonesian military armed force that we call TNI, and also BPBD and also Universitas Patimura for the collaboration in supporting in the field at the time. So we install 11 unit temporary station seismograph, as we can see here, as indicated by red reverse triangles in Ambon Island, in Haruku Island, in Saparua Island, and in Seram Island, combined with the permanent station from BMKG, as indicated by yellow reverse triangles here. And actually, as I said, this is the collaboration between ITB, BNPB, BMKG, BPBD, TNI, Universitas Patimura and Pemprov Maluku, and 4 unit permanent seismograph from BMKG. Thank you very much. And this is the time period of our monitoring from October 18 to December 15, 2019. And this is our team in the field. Yeah, we can see here there were TNI, BMKG, BNPB, ITB, and BPBD, and also Universitas Patimura here. And this is some photos from survey team. Actually, the PIC of the survey team is Pak Dr. David Sahara, yeah, actually. And we can see here, this is the location of station, 11 station. We install around the local BMKG station, around the government and local government, and also around the BPBD office, yeah, at the time. And this is the photos from survey team, the situation during the installation. Thank you very much for the contribution in the field. We can see here this is Pak David, yeah, PIC at the time. Thank you for the hard work, and thank you for the collaboration for all of the teams here. Thank you very much. And then we can see this is the example of the seismogram of aftershock that occurred on November 12, 2019. Yeah, this is the biggest aftershock at the time, with the magnitude 5.1. Actually, this event is located in the Ambon Island, and this is the example of the seismogram that recorded by station in the field. Yeah, actually the instrument we can see here where recorded the weapon is very clear. Yeah, so we can see analyze, we can see use the data for the advanced analysis. And then this is example of the fake weapon of the event, yeah, that occurred on 15 November 2019. Yeah, actually this is recorded by several stations, and the location of the epicenter is located here, as indicated by star green here. And actually this result is under review in tectonic physics by Pak David Sahara et al. And we pick actually the PNS arrival time manually by eye. Yeah, so many students involved for this project, from undergraduate student, master student, and also doctoral student. Thank you very much for the hard work and the collaboration. And this is the Wadati diagram for all FIC event. Yeah, for PNS, we can see here, this is the S minus P travel time versus P travel time, to ensure the quality of the FIC PNS arrival time, and also to obtain the average of the PP over VS ratio. In here we got 1.647. Actually, this is normal. And this is the quantification of our result. This is the time period of observation, October 18 to December 15, 2009, around 56 days. The number of seismograph of 15, and the number detected of aftershock, 1,778 events, and the number of P phase around 10,900, and S phase 10,300 by using software seismogram 2K. And for hypocenter determination, actually there were several steps. First, we determined the initial location by using nonlinear location program, and then we updated the 1D seismic velocity of VP and VS by using VLS, and then we relocate the hypocenter by using the double different method, actually. So this is the result of the location of the aftershock. We can see here, this is a figure A, B, C, and D. Figure A, we use the BMKG station only, and figure B, we use combined BMKG and local station from ITB, and then we determine again the location by using nonlinear location method. And C figure here, we then updated the initial 1D velocity. Actually, the initial we used the 1D velocity from AK135, and then we updated by using VLS, and then we use the updated 1D velocity to redetermine again the location. And finally, we can see here in the figure, we combine BMKG and ITB station and then relocate the event by using double different. And this is the vertical cross-section. And we can see here, it seems there are three clusters during that time period. The cluster 1 in the north part of the main fault, and the cluster 2 in the southern part of the main fault, and the cluster 3 located in Ambon Island. It seems like a trigger event from the main fault here actually. If we see the vertical cross section here from A accent to A, from south to the north, we can see here the focus depth of the aftershock event commonly located at depth of about 5 to 15 kilometers. Actually, it's normal for the crustal event. And this is the cross section B accent from west to the east, and this is a C to C accent from west to the east through the Ambon Island and Haruku Island. And this is the D accent. This is the vertical cross section through the Ambon Island only. And then we use this event data catalog as input for the tomographic inversion. Actually, as I said before, we use 11 broadband seismic temporary station combined with the 2 BMKG station for the tomographic inversion here. And then for the determination of the 3D velocity structure, PP and PPS and hypocenter adjustment, we use code from the CMOV VS to determine PP and PP over VS and also hypocenter adjustment. And this is the vertical cross section for the PP and VS and PPS structure A, B, C, D, E, F. We can see here. And then for the tomographic inversion procedure, actually we have to set up the parameterization model. Actually, we have tried several grid node size, and then we got the optimum grid size node around 10 by 10 by 10 kilometer. And then for the starting model, we start from the 1D updated 1D PP and VS from Veles. And then we can see here we plot the ray path around the study area, passing through the Ambon, passing through the Haruku, Saparua, and also Seram here. Actually, we acknowledge, but the station is not so many actually for the tomographic inversion, but we try to do best to see the subsurface seismic structure, around this area. Actually, we don't know the subsurface previously, the structure around the Ambon, Haruku, and also Saparua. We try to see. Let's see. As a procedure, we determine the damping for PP and PPS ratio, and we got a value of 100 for PP, 100 for the PPPS ratio for the tomographic inversion. And first, we evaluated the resolution in all space model by applying the checkerboard resolution test. Actually, the resolution test not only using the checkerboard test, but also we can use something like a diagonal resolution element, derivative wake sum, ray heat cone, and so on. And actually, we did not plot for the result. Actually, we have already done. And we can see here, this is the horizontal slice for the checkerboard test recovery, for PP, for VS, and for PP over VS at depth of 0 kilometer, 10 kilometer, and 20 kilometer. Actually, our resolution we can see here is fairly relatively good, for the 0 kilometer of sea level, and then for 10 kilometer. Blue and red color here indicated high and low velocity anomalies relative to the 1D initial model that we use as input in the test. And this is the recovery checkerboard test for the vertical slice. This is from the south to the north. Yeah, A profile, B profile, and C profile. You can see here. This is A, B, C. This is for P, PP. This is for VS, and this is for PP over VS recovery checkerboard test. Actually, fairly good for the shallower part. And this is the vertical cross section from west to the east. Yeah, for D profile, for E profile, for F profile, for PP, VS, and ratio PP, VS structure. And blue and red color indicate for high and low anomalies relative to the initial models. And this is the result of our inversion tomographic here. We can see here, this is for the horizontal slice, and this is for PP model, this is PS model, this is ratio PP PS model at depth of 0 kilometer or sea level, 10 kilometer and 20 kilometer. And for PP and VS, blue is high anomaly, red is low anomalies relative to initial model, plotted in the present perturbation. And for PPPS, we plotted on the absolute value. Blue is high value, red is low value. Actually, we can see here at 10 kilometer, we observe some interesting feature. Yeah, we can see here. So the significant feature at 10 kilometer. Yeah, we can see here the white cycle indicate the relocated aftershock, and the dashed black line here. Our interpretation, this is maybe the fault line, yeah. So we can see here, this is the contrast velocity for PP and PS, and also PP-PS ratio here, underline, yeah, between Ambon and also Harakuru Island, yeah, which we suggest as the signature of the fault line. Yeah, clear, yeah. We can see here, this is there are contrast velocity. But of course, we need to investigate. We need to interpret in the more details. And this is actually for the PPPS ratio. Actually, we also observe interesting feature in the tomographic image at depth 10 kilometer, where the aftershock in the north, yeah, we can see here, are located in the low PP, low VS, and also low PPPS. And meanwhile, in the aftershock, in the south, are located in the high PP and also high PS and high PPPS. Yeah, actually, our interpretation maybe this phenomenon between the north and south area may be caused by different fault segment. And then this is the vertical slice, yeah. We can see here, this is from A slice, B, C, D, E, F, yeah. We can see here. In the A cross-section, there is an aftershock cluster on Ambon Island, located on low PP, low VS, and high PPPS ratio. Actually, we suggest there is a possibility of the rule of fluid that drive this trigger event. We can see here, this is A action, yeah. We can see here, aftershock is located in the low PP, low VS, and relatively high PP over VS, yeah, in the Ambon Island. And then in the accent cross section in here, yeah, this is in the northern part. The accent is in the east. This is west. There in the northern part. So the aftershock event located in the low PP and low VS, and also between the high and PPPS, which could be image the geometry of the fault. We can see here some contrast velocity, high and low velocity in PP, yeah, in the vertical cross section. I think this is the interesting feature. And also, this is for the E cross section here. Yeah, we can see here. We can observe the aftershock event located in the low PP and in the contrast of low and the high PS, yeah. However, we observe that in the tomographic image, actually VS, the geometry of the fault is more vertical before it is likely diving to the east. Actually, we can see here, in here is has the diving to the east. In the F accent vertical section, in the southern part, we observe that the aftershock event located in the Ambon, between Ambon and Island, Haruko Island, is in the low PP, high PS, which also show a slightly dipping to the west. The aftershock in the Ambon Island, shown in the western part of the F-accent vertical slice, also has a geometry dipping to the west. And this is the main shock as indicated by yellow star. Yeah, we observed that the main shock of the 2019 is deeper than the aftershock. Yeah, slightly deeper, similar to what happened in Nojima Fault during the Kobe earthquake 95. The 2019 Ambon main shock has a low PP and low VS and also high PPPS anomaly at depth about 12 kilometer. And this is our schematic diagram derived from the PP structure. Actually, we try to understand the fault of geometry derived from tomographic result, derived from the seismicity result using the local earthquake tomography here. Of course, we have to improve, but we have tried to see maybe this is the location of the fault line as indicated by the green area between the Ambon and Haruku. From the north to the south, actually estimated around the 35 kilometer length. And this is the concluding remarks. The local earthquake data recorded by the temporary seismograph from ITB combined with the permanent network from BMKG in Ambon and surrounding area have permitted us to image several important structural features beneath the Ambon, Haruku, and Seram Island, especially at depth less than 20 kilometers. And then we have detected the presence of the contrast velocity anomaly between Ambon, Haruku, Seram Island, which we interpret may be associated to fault plane causing the moment magnitude 6.5, 26 September 2019 Ambon earthquake. Thank you very much. Actually, again, thank you for the collaboration for the BNPB, BMKG, TNI, Patimura University, and also Pemprov Maluku and BNPB. Actually, everybody, if you want to see the video of the installation processes, please visit the site. Yeah, thank you very much for your attention.
Thank you very much, Pak Andri. Don't forget to like and subscribe those YouTube channel.
Not my channel.
Right. Okay, Pak Andri. Thank you for the interesting topic on the 2019 Ambon earthquake. Yeah, so it's very interesting topic. Okay, so any question, please write down in the chat panel. And for Pak Andri and Pak Pil, you can also not to answer in the chat room. Instead, I will give time to answer later, the final minutes after Pak Ilik presentation. We can discuss. Then, okay, we will start to move to the third presenter, Professor Sriwidiantoro. He is currently the head of National Center of Earthquake Studies, or PURSCAN, in Indonesia. And he's also the member of IP, Indonesian Academy of Sciences. And currently, he's the principal of Maranatha Christian University. So without further ado, I will give time 20 minutes for Professor Ilik to present his presentation.
Thank you.
Yours, Pak Ilik.
Thank you, Pak Indra. Good morning, Pak Phil, Pak Andre, Pak Joko, Pak Awali,
Good
and
morning,
everyone. I'll be talking about our project in Bali. It's about integrated geoscience studies for hazard mitigation at the Agung Batur volcanic system. And this project has been sponsored by USAID through the partnerships for enhanced engagement and research program. Actually, I prepared this talk on seismic gaps we observed south of Java, which fits well with the topic of this morning session. But the committee asked me to talk about our studies at Mount Agung. This is the list of the team members They are not only from ITB, but many of them are from the Center for Volcanology and Geological Hazard Mitigation in Bandung, as well as from VDAP, Volcano Disaster Assistance Program, USGS. Actually, we already presented some of our results at the AGU Pol meeting last year. Jeremy Pasicek was present. Also, Jacob Lowenstern was present. And some of our researchers went to San Francisco last year. We plan that the rest of our team members will go to San Francisco this year, but unfortunately, due to COVID-19, it will be online, like what we have this morning. So, the scheme of the proposed integrated studies includes fieldwork campaigns, integrated analysis, and outreach events. For fieldwork campaigns, we have installed 25 new seismic stations, thanks to Pak Phil, that allows us to use your seismometers. And we also installed 4 new GPS stations from ITB, and the rest of the GPS stations belong to CPGMH. And we also conducted geological and volcanological survey as well as structural mapping. And for the analysis, we have conducted volcanoseismology, volcano deformation, geomechanics, and geological analysis. And for this project, outreach events are very important. So we have conducted some training and workshop, volcano schools, and conferences on Agung, as well as publications. This is our study area, Bali, you know very well, and the reverse black triangles depict our seismic stations locations. These are pictures from Pak Zulfakrisa when they installed our instruments. And you can see some examples of the waveform data. We can see quite clearly the arrival of D and S phases, the distribution of earthquakes is shown in this figure, and we obtained the BBVS ratio using this data is 1.7 from the Wadati diagram. And Pak Zulfakrisa and co-workers, including Pak Phil, has published a publication on tomographic imaging of the Agung Batur volcano complex using ambient seismic noise. And we have submitted to other manuscripts on imaging the subsurface structure of Mount Agung using volcanotectonic earthquake tomography. I'll be showing the result in a moment. And David Sahara and co-workers also submitted a manuscript on analysis of volcanotectonic events preceding the 2017 Agung volcano eruption using a local seismic network. And Pak Indra Gunawan and his co-workers is preparing a paper on investigating the pressure source beneath Mount Agung from December 2018 to March 2019. This is the early period of our project. They use continuous GPS data. All right, from ambient noise tomography, it's already published. We observe a quite interesting feature from group velocity structure. We observe this very pronounced low velocity located between Mount Batur and Mount Agung. And from the depth inversion results, we can see the extent of the low velocity anomaly. Our main results include this low velocity underlying the volcanic complex, as I said, between Mount Agung and Mount Batur at depths up to about 2 kilometers. And it was interpreted due to a combination of low PS volcanic deposits, as well as the presence of over-pressurized hydrothermal fluid systems at shallow depths associated with magma fluids and or gases, which may have been produced by magma intrusion at depths greater than 7 kilometers or so, as explained by Albino and co-workers, as well as by Shahbana and co-workers in 2019. From body wave tomography, using the PT event data, we have successfully localized a magma reservoir as indicated by high BPVS ratio. The BPVS ratio in this region is about 1.85, quite high. Within a low seismicity zone at depths between 2 to 5 kilometers below the volcano summit. And we also confirmed the presence of sub-vertical dike at depths between 8 to 14 kilometers with a high BPVS ratio, where most of the recorded volcano tectonic events originated around this anomalous region before the 2017 eruption. So this is our conceptual model. We have a shallow reservoir here beneath the summit, and we observe, or we interpret it as dike intrusion. This is similar what has been published by Albino et al. At Nature Communications 2019. And then David Sahara has analyzed the events during the seismic crisis in late 2018. I will show the result, which is quite interesting. David and co-workers have used more than 2,700 volcanotectonic events with 1,300 P and almost 1,200 S wave phases, which were successfully identified. Here are some vertical cross sections through Agung and Mount Batur. We can see here that many events are located between Batur and Agung as confirmed by the tomographic models. And for GPS campaign, we have installed 4 GPS stations at these points. This map shows the deformation pattern before the eruption of the 22nd January 2019. And CVGMH also already installed prior to our project some GPS stations. So combined with our new stations, we have 7 GPS stations. This is preliminary results by Dr. Indra Gunawan showing the inflation, deflation prior to the December 2019 eruption. Red means inflations before the eruption, and blue depicts the deflation during the eruption. This is the horizontal deformation, and on the right hand side is the vertical deformation. Again, red depicts inflation, blue depicts deflation prior and during the eruption. So that's what we have done with the data, and we have participated in quite many conferences. This year we have submitted 5 abstracts to be presented at the AGU fall meeting. And as I mentioned before, we went to San Francisco last year, presenting 8 papers, and at the AOGS last year, also at the Haki annual meeting this year, we presented quite many papers out of our research results. But as I mentioned before, for peer projects, dissemination events are very important. So we also have conducted online seminar series in June 2020 this year. The first week was about seismicity and tomographic imaging of the Agung volcano, and then followed by deformation of the Agung volcano and geo-virtual of the Agung volcano from the surface to the deep, conducted by our colleagues from the Department of Geology, ITB. Here are some examples of our outreach events. We gave seminars to several elementary schools around the Agung volcano. This is at the Bandem Elementary School. We are facing southwest, so the school is located at the foot of the Agung volcano to the southeast. And our project is supposed to be ended last September this year, but due to the COVID-19 pandemic, the project end date has been extended through end of June next year. So during the upcoming few months, we will hopefully be able to conduct outreach events again next year. And of course, we would like to finish some more papers. And as I mentioned before, we will present some of our research results at the HU fall meeting next month. Thank you.
Okay, thank you, Pak Ilik, for sharing the research project of PIR. Okay, right now I'm going to open a question and answer session. So anyone who wish to ask question, you can write down in chat, And if you want to be anonymous, yeah, you can share privately to me. And okay, so if I have already some question sent privately to me, so I will share my screen for the speakers to see. Right. I hope you can see this slide. Papil, can you see my screen?
Yeah, I can see it.
Okay, so the first question is for Professor Phil Cummings. The question is there any established study on tomography support the model? So that is the first question, and please, I give you time to answer. I will stop. Please, Papil.
Okay. Well, there are studies that reveal the main structure is the slabs. And so it doesn't really, it's not really clear from those studies that there's necessarily movement along the band of detachment. It doesn't really show up. That's a very shallow structure that doesn't really show up in any tomography that I've seen. And you can't really get the station spacing there since it's, it's under the water. So it's difficult to get, I think, the station spacing you would need to resolve that. You can resolve the slabs under the band of C, but that, that's there, whether it's rolling back or whether it's actually the two slab model is actually sort of difficult to determine, I think, from the tomographic models I've seen. Both of them have sort of, high velocity slabs that come down beneath the band of C, and whether it's two slabs or one slab is sort of, I don't think is easy to resolve from the models that I've seen.
Okay. Okay, thank you, Papil. I hope that's answered the question about the slab in the bandasi. And second question goes for Professor Andri. The question is, anonymous, what is the error of earthquake position after relocation? Is there ellipse error of the earthquake location? Yeah, please,
Sorry.
Andri.
Thank you, Pak Indra. Thank you for the question.
Yes.
Yeah, actually, we have already calculated for the error using the bootstrap and also ellipse, yeah, for the initial location and also for the relocated event. Both already done. Actually, for the more information, actually, we can write the paper from Pak David Sahar et al. Yeah, under review in Tectonophysics.
Under review, okay.
Yeah. Thank you, Pak Indra. Thank you for the question.
Okay, thank you, Pak Andri. So detail can be found in Pak David Sahara under review paper in Tectonophysics. I hope it will be available soon.
Yeah.
Right. Okay. Now let's move on to the next question. What is it? Okay. For Professor Sriwidiantoro, the question again anonymous. Question is: local partnership with universities in Bali is important for increasing capacity of local scientists. Oh, okay. So, do you have partnership with local universities in your project? Okay, please, Pak Ilik.
Thank you. Well, we have partnerships or we collaborate with local governments, and we have collaborated with Balinese scientist, yeah, Kadek. He was one of our students, and of course, we would be very happy to be able to develop a partnership with Udayana University, for instance. But so far, what I know, at least, in Udayana, there is no geophysics nor geological department. So we have been working with Kadek, actually. from Bali, but he's not a staff member there, but he plans to become a staff member at Udayana University. Okay.
Oh,
Thanks.
okay. Thank you, Pak Elik, for the answer. So we hope that by collaborating with Balinese scientists, which can improve through Mr. Kadek and increase also the capacity of scientists in Udayana University. So I hope that answered the question. And then I will move on to the another question. For example, from Ervin Eli, goes for Pak Pil. He or she question about what is your opinion about displacement 5 kilometer in Weber Deep, Banda C slide 20, and what point meaning hyperextended lithosphere in Weber Deep, because complex interplay between crustal. Pak Pil already answered through the
yeah, I can answer that. I'm not sure what the 5
Yeah.
kilometer came from, but there were the numbers that I used to describe it were there's roughly 120 kilometer width to the Weber Deep. It's thought to have opened over the past 2 million years, so that results in about on average a 6 centimeter per year slip rate. And so that 5 could have come from the 5 centimeter per year I used in the figure, which was actually wrong. It's actually should have been 6 centimeter in the figure, and that's where it comes from. What is meant by hyperextended lithosphere? Well, it's thought that lithosphere below at the base of the Weber Deep is hyperextended. That's mainly comes from my colleague Jonathan Powell.
Okay, so I hope Ervin got the information very well, and if he or she wants to answer or post another question, please put in chat menu. And then also another question goes for Pak Pil from Pak Mudrik Daryono from LIPI. I hope he's doing okay now. How are you, Pak Mudrik? His question is there evidence of morphology deformation on island or undersea? And Pak Pil already answered, but maybe if you would like to add more comments on this question, Pak Pil, please.
Well, I'll just elaborate a little, and I'll apologize for misspelling Pak Mudrik's name. I just was typing very quickly. Thank you for the question, Pak Mudrik. And yeah, that's really a question for my colleague Jonathan Powell. And it's described in much more detail in some of the papers by him that are referenced in the Nature Geoscience article. But yeah, one of the first things that made him realize that the interpretation of the Weber Deep as a massive fault scarp, basically, for the bonded detachment, were the lineants, these lineations at the base of the Weber Deep that can be seen in the detailed bathymetry that he got, that Robert Hall got, I think from some proprietary exploration company, that aligns perfectly with the inferred opening direction of the Weber Deep, and I think aligns also with directions along the Kawa shear fault. And then, of course, there were the scarps on the eastern side of the Weber Deep that I showed the photos of, and he's got other evidence in his papers for that interpretation.
Right. Okay. Thank you, Pak Pil, for the question. Anyone who wants to ask directly, you can raise your hand and start to unclick the button mute on the left side of the panel in Zoom. And okay, I will pose another question. Where is it? Okay, let me. Okay, just give me time. So we still have about 10 minutes for question and answer.
I have a question for Pakilik.
Oh, please.
Pakilik, it was very, very impressive to have the outreach that you described in your project. But I also wonder what what outputs from the product do you think will help to try to mitigate further volcanic disasters at Mount Agung? For example, will the 3D velocity model be used to help Baranggyalagi locate earthquakes more precisely, or can you just comment on how the scientific results might contribute to disaster mitigation and monitoring of the volcanoes?
Thank you, Pavel, for your questions. Well, I have many co-authors here. Perhaps Pak Andre, Pak Devi. Is Pak Devi here? And also Pak Indra Gunawan, of course, from the GPS point of view. Will our colleagues from PVMBG use our results? As long as I remember, within this project, Pak Phil, 3 students coming from the CVGHM are studying at ITB using this data, the data from the project, which is kind of direct use of the project by them. But yeah, of course, I hope that our result, like the 3D velocity, as you mentioned, it can be used to locate events, future events by CVGHM, yeah, because we always have new data, new events to be determined that would be useful. Pak Andre, Pak Indra, would you add some comments on it, please?
Okay. Thank you very much, Pak Pil, Pak Ilik. Actually, from the seismology side, we record the data from the December 2018 to around August 2019. From those data, we try to see the seismicity around the Agung and Batur volcano system, and also to see the subsurface structure through the ambient noise tomography and also travel time tomography. And also we have another data set, actually not from peer project, but from the PPMBG station, permanent station actually, for the 2017, during the Agung crisis, from the September 2017 to December 2017. And the tomographic inversion result from the data, from this data already submitted to the international journal by Ardianto et al. Actually, Ardianto is here. He is a master student supported by peer project at ITB. And the result actually, of course, we can use the result of the velocity structure for the future study, something like to hypocenter determination around the VT in Agung and Batur volcano, and also and so on. And then the current study from the Martanto, from the PPMBG, actually now he is in geophysical engineering study program at ITB. He is developing, he has been developing about the DNA seismic software to classify the waveform from the various of the seismicity in Agung automatically, so it can be reduce the time to analyze the type of event in the volcano area. I think that's all that I had. Thank you.
Thank you.
Yeah, thank you, Pak Pil, for your question. Okay, if no one posts in chat, I have question sent to me privately again. Let me share screen again. Okay. This is for Professor Andri Dianugraha. The question is, if the main shock of the Ambon earthquake is deeper than the aftershock. So what is the elastic depth of the fault?
Okay, thank you, Faendra. Thank you for the question. It's hard question. Actually, normally,
Yes.
maybe everybody knows. Actually, for the crustal event in the continental crust, actually, average the depth of focus of the event less than around 20 kilometer. That we call maybe still brittle rock. Yeah. Now below the 20 kilometer, actually, for the crustal event is not so often. Yeah. Maybe due to the something like elastic that we call something like that. So yeah, on average, less than 20 kilometer for the focus depth of the crustal event that we can see in the Ambon earthquake from our study, and also for the study from the BMKG. We can see here the distribution of the main shock, and also the aftershock focus depth less than on average 20 kilometer. Thank you.
Okay. Thank you, Pak Andri, for the answer. I hope that's answered the question. Right. So we still have another 5 minutes. So I will share again the next question posted from Anonymous for Professor Sriwidiantoro. Pak Ilik, the question is from seismic is the source magma? What is the meaning? From seismic is the source magma, or the magma is deeper? Oh, probably the question is about the earthquake as you shown in the slide. Is it the earthquake happened because of magma source, or the magma is actually deeper? Probably that's the meaning of this question.
All right. As I mentioned before, for tomographic imaging, we use the volcanotectonic data. So we only can image the upper part of the magma body, if that's true. So indeed, we localized a quite shallow magma body around 2 to 5 kilometers. But I believe there must be a deeper magma source as presented by Albino and co-workers at the Nature Communications paper, around 20 to 25 kilometers depth. But using the VT data as we have conducted, we cannot image that deep anomaly. Perhaps Pak Andre, who has conducted body tomography using the regional data, can add some explanation. Did you image quite well the deeper part of the magma body? Pak Andre, please.
Okay, thank you, Pak Ilik. Thank you for the question. Actually, from the data in 2017 from Ardianto et al., we can observe the high PP per VS ratio beneath the Agung, at several depth. From the high PPVS ratio zone, we can estimate, we can interpret maybe associated with the hot material or something, maybe hot material, maybe magma source. But for the deeper magma, actually from our tomographic result, the resolution is not so cover the deeper part because the PT even is shallower, so the ray part may be not passing through the deeper part. But at least we can see the intermediate heat source and also shallow source maybe related to something like that we call the magma source. From the data of 2017. But from the ambient noise tomography from Pak Zulfakrija result, we observe also the low velocity of VS between Agung and Batur at shallower depth, maybe less than 2 kilometers, Pak Zul, Maybe we can interpret maybe this feature may be related to something like the hydrothermal, something like that, but not related to something like maybe magma knot, something like that. But still, for the deeper magma, we cannot resolve for this time. Actually, maybe because our network is not so wide and the event is shallower part. Thank you.
Thank you, Pak Andri and Pak Ilik, for the answer. Right, so I will share another final question sent to me for Prof. Pak Ilik, Pak Pil, sorry. The question is, tsunami modeling depends on the slip. If using single slip model, would tsunami differ with the heterogeneous slip model? Probably what it means is that the different slip, for example, heterogeneous slip, will make a different tsunami height compared to this single slip. What is your comments? And if the landslide tsunami and landslide cause tsunami, how far is the distance the landslide region with the source of the earthquake, maybe? Okay, Pak Pil, it is a question for you. Pak Pil?
Sorry, I was on mute. Yeah,
Okay.
for the heterogeneous slip, we didn't experiment with heterogeneous slip models, but we did experiment with a lot of different homogeneous slip models. And I think overall, I would say that it's very difficult to produce the large tsunami with an earthquake slip model. Either the amplitude's not big enough, and/or the polarity of the initial tsunami is not right. In fact, it's just, from all the things we tried, and we did try a lot of things, we just couldn't do that. And then regarding the landslide, it's about 250 kilometers away, so it is considerable distance between the landslide and the earthquake. But we still think that is based on the study in the U.S., for that was admittedly a quite different geographic region, that it's reasonable to have triggering of landslides even at that distance, even if for magnitude 7.5 at 250 kilometers distance. Now, it's difficult to say what the lower bound would be on the triggering, but landslides can happen spontaneously depending on the slope and the competency of the sedimentary body. So you could have relatively small earthquakes even at some distance triggering landslides. I think it's a difficult question. I think it's difficult to say that earthquake could not have triggered that landslide, because it depends so much on the instability in the landslide. But we don't think it is unreasonable. It is a considerable distance, but we don't think it was unreasonable to suppose it could have happened.
Okay, thank you, Pak Pil, for the answer. And we have reached the final minutes, the end of the time of this session. So I hope every question answered can be received by the questioner. And so I thank you all for your presence in this session, and I really hope that information presented here is very useful for all of us regarding the Bandasi and then the Ambon earthquake and also the Agung Batur volcanic activity. So let us give a big applause for the presenter, Pak Pil, Pak Ilik, and Pak Andri.
Thank you for all.
Thank you. Thank you, Pak Pil.
Thank you, Pak Pil.
Thank you, everyone.
Thank you, everyone.
Ilik and Pak Andri, thank you very much.
Thank you.
When will you visit Bandung, Pak Pil?
As soon as I can, but
Okay, good.
I can't leave Australia at the moment.
Okay.
As soon as I
We are
can,
waiting in Bandung, Pak Pil.
I want to come soon.
Okay, so I'm going to close this session. So I thank you all for your presence here again, and please stay healthy and stay safe in this pandemic condition, which seems like never-ending pandemic condition. But let's stay healthy. So I close this session. Thank you very much.
Thank you.
Have a
Thank
good day.
you.
Here.
Stay healthy and happy.
Thank you.
You too, Pak Ilik.
Okay, take care.
Thank you, Pak Indra.
Thank you, Pak Phil. Thank you, Pak Andri.
Okay.